switch on. Okay. This is me. Rishabh, are you here? Rishabh Pandey? Is it audible?
For student should be on.
Yes, sir. It's clear. Okay. So, Rishabh, tell me, what's your question?
To hear you.
We couldn't hear you.
Sir, actually, I was muted, sir. I was muted. I'm
Yeah,
sorry.
yeah, unmuted. No, okay. Go ahead. Tell me your question, please.
Sir, I actually am not here for question. I just saw that there was going to be an online session, and I just wanted to interact with you for a little bit. So that's why I'm here.
Okay,
Actually,
welcome. This session is mainly you can, of course, you are welcome to listen. If you have any question, you can also raise and I would answer. Or if somebody raises a question, I would answer them. You can also continue to listen. No problem.
yeah, sir. So first of all, thank you for this course, sir. I mean, I have been struggling with graphs for a very long time now because the terminologies and the standard literature which is available about graphs, it's heavily confusing. And even the professors in my university, I mean, I just don't get these algorithms. But after I've been in these classes, the walks and paths, that difference and the relation. I mean, that has been phenomenal for me, sir. So thank you for
Excellent.
this course.
Welcome. So if you have any other general question until somebody comes, I can probably
Sir,
explain to
actually,
you or
I do have a
clarify.
question, sir.
Yeah.
Sir, actually, I am a third year student right now
Hmm.
from BTech Computer Science.
Hmm.
So I just gave GATE Computer Science this year in 2025,
Hmm.
and I got All India rank 1763.
Hmm.
But actually, it's not enough for me to get into IISc. I dream of being into IISc someday.
Hmm.
So, what advice would you give me, sir, so that I, along with my gate prep, I can also keep enhancing my mathematical skills.
Uh, that's a little too personal. Uh, Maybe you have my email address.
I don't think so, sir.
Okay, I'll give my email address pirangan55@gmail.com.
Of course, sir.
1 second. She is typing my pirangan55@gmail.com. Okay. So to this
Thank you, sir.
email address, you send your query. I will handle them off the meeting because this meeting is, I mean, it may not be appropriate
No
to
problem,
discuss
sir.
the
Thank you, sir.
personal
Thank you.
detail, but surely I'm going to answer your questions of the thing. And you sent a mail to me asking clearly what question you have in your mind. I will answer them through mail as well. Okay.
Okay, sir. Okay. Thank you,
Okay,
sir.
welcome Arnav and welcome Kavita. Do you have questions? Any question or any question, topic you want to revise or explain or generally I'm available for this online meeting, but you can unmute and then talk to me if you have any question. Are you able to hear me?
Yes, sir, your voice is audible, sir. I
Okay,
have a doubt, sir.
yeah, go ahead, tell me.
Sir, you have explained the walk and path and the Bellman equation between walk and path.
Right,
Please revise those concepts, sir.
okay,
For example, you have found for the Q of alpha of 0, alpha of 1, and up to alpha of n minus 1.
right.
Since if you have n vertices, you might have n minus 1 edges. You
Hmm.
have derived some conclusion from that derivation, sir. Please revise those concepts.
No
Since
problem.
in the second part of your video,
Okay,
some 5 lines of explanations were missing in the lecture video, sir.
is that right? I
Yes,
have
sir.
to check in that case.
Yes, sir. I'll
Yeah,
mail you, sir. In week
okay.
3, we have 2 parts of video.
Hmm.
And in second video, the continuation is coming from the second video. The beginning part, a few lines were missing in the video recorded session, sir.
Okay. We are noting it down. we will just check at our end
Thank
what
you, sir.
happened to that.
Really, your class is very interesting. I'm taking all the notes completely, sir. Thank you for your wonderful lecture.
Oh, welcome. Warm appreciations, and then thank you very much. And now, see if I have to write on the screen, what do I do? Because they can see what I write on the screen, right? One second, I'll go to the screen and then right.
Just write.
Okay,
Something.
I'll
Sorry.
just check with them. Are you able to read what I have written here on the screen?
Yes, sir, it's clear. We can see it.
Yeah, one of you, Rishabh, you could see. Kavita, are you able to see what, Arnav, are you able to see what is written here?
Yes,
on
sir.
the-
The screen is visible to me. I'm listening, sir.
All right, okay. If the screen is visible, okay, good. So we are interested in finding the shortest path, weight of the shortest path from, so let's say weight of shortest path from S to a vertex V. This is what we want to find. And the notation we are using is a delta SV. Since S is fixed, we can write a simplified notation of delta V. But this we are going to find in stages, right? That is because the, what do you mean by shortest path? Each path has got a weight of a path. And I want the minimum weight of a path, where P belongs to set of all paths from S to V. So from S to V, there are several paths. Let us say this is S. This is one path to V. This is another path to V. This is yet another path. Each path has a weight, and we are interested in the shortest path. That is the minimum weight path. One approach is I split this set, okay, in the following way. I view the set in the following way. Set of all paths with one edge. All paths from S to V. From S to V. With two edges. With three edges. Right? So, for example, this is S. There is a direct connection to V. There is another path like this. This has got two edges. There may be another path. This may be 1, 2, 3, 4 edges. So like this, you have paths that are containing a certain number of edges. When you are considering the paths, the maximum number of edges you can have is n minus 1, right? S to something, something to something, and then finally to V. Sharing your screen. Okay. Oh, here I am pressing something. All right. So this is S, this is V. All vertices, even if they have, you can have only n minus 1 edges. Therefore, set of all paths with one edge, something like this. Set of all paths with two edges. There may be several paths with two edges. This is another path with the two edges. This may be another path with the two edges. So there will be several paths with two edges. There may be several paths with the three edges, and so on. Now, I want to find the minimum in this collection. The minimum in this collection. And the minimum in this collection. Like that, I want to find the minimum in these collections. Okay? Why do I find that? I will tell you the simple reason why we are going this way. When we go this way, they are all related that it is easy for me to compute the minimums. Okay, so let's go to the next page. How do I go to the next? This one? No, this is Zoom. How do I go to the? One second, Kavita. I want to go to the next page and explain. Page 1. Next page. Add page, add page. Page 2 has come. Right. Okay. So let us define the following. Okay. Let P, K, V is set of all paths from S to V with at most K edges. That means you have P1 with at most one edge. P2 with at most two edge means with one edge and two edge. So all paths in P1 is included in P2 and P3. In this way, you are going to have Pn minus 1. Pn minus 1 is set of all paths with at most n minus 1 edges. That means, oh my goodness, this is horrible. All kinds of things are, I have to write here, but is there a way to remove this? Okay, can you close that? End the session, huh? Ayo. No, I want because if I write, other things are popping out. Okay, let us see next time these commands you put in the left so that when I write, my hand doesn't touch other commands. Okay. Set of all, this is set of all paths. We want the, my goodness, look at this. Something has happened. Okay, this is set of all paths. So I want the minimum in this set. Every path has a weight. All paths, every path will have a weight, and I want the minimum. Okay, so the way in which I find it is, if you consider all paths, that will be a lot of paths. So first I consider the minimum here. Then I see how to extend that to the minimum in this set. Then I consider how to extend the minimum into the bigger set. Okay, that is because of the following reason. If A is contained in B, minimum in A will be greater than or equal to minimum in B, because B is a bigger set, right? It may have a smaller value. For example, if A has got 7, 9, and 10, the minimum is 7, but I consider a bigger set. If the bigger set has got only 23, 41, still 7 is the minimum in B. But if the bigger set has got 3, then 3 is the minimum. In other words, minimum of B can be smaller or it can be same. So minimum of this and minimum of this, how are they connected? P1 is a superset. It is set of all paths containing 1 or 2 edges, and so on. Therefore, how do I find the minimum for this? How do I relate to the minimum of this? Once I do that, same way, I relate the minimum of P2 to P3, minimum of P3 to P4. In this way, I will proceed and then I will find the minimum of Pn minus 1. That is what Bellman equation is doing. What Bellman equation is doing is, if the minimum of Pi is available, how do I use it to find the minimum of Pi plus 1? That is the crucial step. That can be repeatedly applied. Minimum of 1 is very easy to apply, right? Because what is minimum of 1? At most to one edge. If the edge is there, that is the only path. Therefore, P1 will have only one entry. The minimum is just that entry, namely weight of that edge. S to V, there is an edge. If the weight is 3, this is P1, at most one edge. Yes, it has got one edge. And if the weight is 3, then the minimum is 3. That's all. So P1 is directly computed. How do I use P1 to compute P2? How do I use P2 to compute P3? Right? That is what Bellman equation is doing. Very simple argument of relating the Bellman equation of Pi to Pi minus 1. All right. The same thing we are going to do for walks. We can do this for path. We can do this for walks. Walks are also classified. Can we go to the next page? Add a page. I can define like this: walk Kn, Wkn equal to, all right, set of all walks from S to V with at most K edges. Now we have introduced two notation. For PKV, the minimum is delta KV. For WKV, the minimum is called alpha KV. Now what we have shown in very simple terms is how I can compute alpha KV from alpha K minus 1V. How do we do that? Similarly, how do I compute delta KV from delta K minus 1? These are defined by the Bellman equation. If you look into the Bellman equation, this is exactly what is done. Once I know this, I can repeat this step. Suppose I know how to find alpha K from alpha K minus 1. Then from alpha 1, I can get alpha 2, applying this procedure. From alpha 2, I can get alpha 3. In this way, I can keep on getting the values. Similarly, I can do for delta K. The Bellman equation and its proof is simply relating this. Okay. So should I explain before I explain that to Kavita? Or now, Rishabh, you have any other question, any clarification that is needed?
No, sir. Actually, the set thing that you just explained, that Pn minus 1 till Pn minus 1 thing, that is actually what was bothering me in the first week. That was the last video and the last part, but now it's clear actually because that superset property. So
Yes.
I like it.
Because of the superset, it becomes smaller and smaller and smaller, and the shortest path weight you get finally using that formula. In the step, if you proceed, you will get the last value, and the last value is what you want. That you can only gradually proceed. You cannot jump over. There is no way I can get alpha 3, then alpha 10, then alpha 43 and all. I can get only alpha 3 from alpha 2. I can get alpha 4 only from alpha 3. Like this, the relation is connecting alpha k with alpha k minus 1, delta k with delta k minus 1. Based on this relation, you repeatedly, iteratively, you compute, and when n minus 1 is reached, you stop and output that result. That is the outline of the idea. Okay. So, Kavita, have I answered all your questions, or do you have any other, or should I explain a little more on how Bellman equation actually derived? MP Palanivel, you have joined. You have any question, Palanivel? I'm not able to hear. Kavita, are you able to hear me? You are muted. I'm not able to hear whatever you are saying. Or you can type.
Hello, hello, sir.
Yes?
Yes, no doubt, sir. No doubt.
It's clear, no? Okay.
Yes, clear, sir.
Thank you. Any
Sir,
questions? Anything that you have, please ask me. I will illustrate, explain.
actually, I had a question, sir.
Yes, please, go ahead.
Sir, in one of your videos, we said that the convergence of the alpha k values
Yeah,
is same as the delta k values.
yeah.
So why is it? And we tried to work with alpha k values to actually get delta k values. So why is it easier to work with alpha k values and not delta k values? What is stopping us from that, sir?
Delta k values are equal to alpha k values only if the graph has no negative cycle. Otherwise, their values are different. Okay, I will write down then. Let us note this. Alpha kv is equal to delta kv if and only if G has no negative cycle. If G has a negative cycle, these two are different. This is if and only if. If G has negative cycle, then alpha kv is not equal to delta kv. There is no guarantee. Sometimes it may be equal, that may not be equal. Alpha kv can be computed for all graphs. Whether G has a negative cycle or not, I can compute alpha kv. Delta kv, I cannot compute for the graph. I mean, delta kv doesn't have the formula. Only alpha kv has the formula. Therefore, what I do is the following, right? I will write down that. I can compute alpha kv for any graph, because property of alpha kv is not depending on whether there is a negative cycle or not. Okay. Therefore, when a graph is given, you do not know even whether the graph is a negative cycle or not. That is not known. If somebody says it doesn't have a negative cycle, it is fine. But if is simply given a graph, you do not know whether it is a negative cycle or it has a negative cycle or not. Therefore, you cannot compute delta kv values at all on the graph whose properties are not known. Whereas alpha kv, I can compute for all graphs. Suppose G has no negative cycle, then if G has no negative cycle, then alpha kv is equal to delta kv. Because of this, on a graph that has no negative cycle, my alpha k computing algorithm turns out to be delta kv computing algorithm. Therefore, alpha n minus 1v computation is actually delta n minus 1v computation, which is equal to delta v. Therefore, I am computing delta v only through alpha v's. Suppose I have given you a graph that has a negative cycle. While I can compute alpha k v for k equal to 1, 2, n minus 1, n minus 2, any value I can keep computing it because of the recurrence equation. But I cannot compute delta k values at all because they are not related. And do I have a direct formula for delta? No, I don't have any formula for delta kv. Since I do not have a delta kv formula, and since I have only alpha kv formula, I compute alpha kv for the graph in which alpha kv equal to delta kv, I have solved the problem. For other graphs, I do not have a solution. Therefore, shortest path problem is solved only in the graph that has no negative cycle. If you give me a graph that has a negative cycle, finding the shortest path problem is very hard. In computer science terminology, it is NP complete. None of the algorithm we have studied in the course will work. So I will write that if G has a negative cycle, we do not have any algo that we studied works. It doesn't work. We do not have anything that works. Or none of the algorithm works. We'll put it that way. None of what we discussed works on G that has negative cycle. Therefore, this is one important constraint. All shortest path problems are solved only in a graph that has got no negative cycle. If a graph has a negative cycle, I cannot solve shortest path problem efficiently, and there is no clever solution available. All the algorithm that we worked doesn't work for the graph with the negative cycle. Remember that point basically. Okay, suppose I have given you a graph that has no negative cycle. Suppose if I know that this is the property of the input, how do I find delta value? I'm going to find delta value. I don't have a recurrence equation for delta value, but I have a recurrence equation for alpha value. So I will compute only alpha value on that graph. But since alpha equal to delta, it turns out that I am actually able to compute delta value in that. That is the reason why I am taking the route always through alpha. I have recurrence equation only for alpha. I can compute only alpha value. If alpha values are not useful, nothing can be done. But alpha values are useful for our problem if G has no negative cycle. Why? If G has no negative cycle, alpha value equal to delta value. And delta value is what we want. So I go about working on alpha values, which is actually computing for me what I want. Therefore, algorithms work on computing alpha values. Have I made myself clear?
Yes, pretty much. And just two observations that I've drawn from this is that the first thing that I wanted to say is that let's say I've been given the information that the graph has no negative cycle. So in the recurrence relation for alpha values, can I replace alpha with delta? Is that good?
You can, because if G is given as no negative cycle, alpha equal to delta, therefore you can simply say that computing alpha value is same as computing delta value. Therefore, after n minus 1 step, you are going to stop. Yes.
Yes, and the second observation is that first of all, make sure that the graph has no negative cycle, and then the every shortest walk is the shortest path, because then we can remove the positive and negative zero edge cycles, and
in fact,
it would
that
be
is the reason why
shortest
alpha
path.
equal to delta. That is
Yes, sir.
exactly the reason why alpha equal to delta.
Yes, sir. Yes, sir. Thank you, sir.
Welcome. Yes, Bibu Rawat, any question?
Yes, sir. Hello.
Yeah, go ahead.
Yeah,
I'm able
so
to hear me.
I have one doubt in Johnson's algorithm.
Yeah.
So yeah. So in Jensen algorithm, first we do that. First we use Bellman-Ford to modify our weight function,
Yes,
and then we solve our problem ASP by Distrust algorithm.
that's
Okay.
right. Because
Yeah.
we have
So
reweighted, and in the reweighted case, all weights have become positive.
yeah.
Earlier, the weights can be anything, and Dijkstra's algorithm cannot be used if even one edge has negative weight.
Yeah.
Whereas Johnson's algorithm works for all kinds of weights. It works for all kinds of weights.
Yeah.
So how do I make it work? First, I convert that into something that has no negative. But if you mindlessly do a translation, then the shortest path may not be preserved. What I mean is, the shortest path in the original graph and shortest path in the transformed graph may be different. In that case, there's no point in solving the shortest path in the transformed graph. What we want is the transformed graph also should have the same shortest path. Now, the transformed graph has the same shortest path, but weights are positive. So I applied Dijkstra's algorithm to solve the shortest path problem and output the same path as an output for my original problem.
Yeah.
Therefore,
Sorry.
the key thing is maintenance of the path.
Yeah, sorry to interrupt you. I think for Distrust algorithm, the weight of every edge should be positive, na? Or it may be zero.
Which one? Weight of
Uh,
what?
Weight of an edge should be positive for applying
For applying
Distrust,
Dijkstra's algorithm, it should be positive.
isn't
So
it?
what we do is, we first do Bellman and Ford and get that estimate, then do the transformation of subtracting that from that original weight, which makes the thing positive.
Yeah, so we use Bellman-Ford equation to modify our weight function.
Yeah,
And
exactly.
yeah, in lecture, we did that thing that the modified weight function has a weight greater or equal to 0.
Yes.
We didn't do that thing that modify weight function have a weight greater than 0 for every age. So how we can apply the Distrust algorithm for the modify weight function? It
Oh,
should be
okay. Well, one thing that we can do is, Dijkstra's algorithm actually works when you have the weight greater than or equal to 0. Only thing is that negative weight edge should not be there. 0 edge is not causing a problem, right? It is the 0 cycle that will cause a problem. It will still find a solution. Solution will not be unique. So to avoid the 0 cycle, well, 0 cycle will not be, it should have only zeros because all weights are greater than or equal to 0, right? Therefore, we will ignore that case and consider that our algorithm can be made to work using Dijkstra's algorithm. 1 0 edge is not going to cause any problem. 1 or more 0 edges. It should not form a 0 cycle. In general, that won't be the case. Therefore, we can apply Dijkstra's algorithm. Yeah, where is the question here?
On the times calculator. Please tell me.
Okay. Now I will give an explanation for the way in which alpha values are related. Okay. What is alpha? Let us write. Alpha KV is minimum among the weights of the walks from S to V with at most K edges. Okay. This is the definition of alpha KV. Now consider a walk of minimum weight with K edges from S to V. Let UV be the last edge. So totally you have less than or equal to K edges. This is a walk, and this walk has got a minimum weight. So what is the weight of this walk? Weight of this walk is alpha KV. That is the weight of the whole walk. This is a minimum walk. I am considering a minimum walk and its weight is alpha kV. Okay. Consider the walk from S to U and UV be the last edge. Right. Now, what can you say about this is a walk from S to U. How many edges are there? Less than or equal to K minus 1 edges. Less than or equal to K minus 1 edges. Because the whole thing has got less than or equal to K edges, I have avoided the last edge. So one edge is ignored. So how many rest? Less than or equal to K minus 1 edges. This must be the shortest walk. If this is not the shortest walk, I can replace it with a shorter walk, and that is a contradiction to the minimality of the whole thing. The whole thing is minimum means this must be minimum, the part, right? Therefore, it is a walk and it's a walk with the minimum weight. Therefore, its weight is alpha K minus 1 U. Alpha K minus 1 U, because it has got less than or equal to, it is the minimum weight. There it is from S to U. Therefore, it is alpha K minus 1 U. That means alpha kV is equal to alpha K minus 1 U plus this part plus weight of this edge, weight of U. This is the relation between alpha K values and alpha K minus 1 values. Suppose the vertices are V1, V2, Vn. I have alpha K minus 1 V1, alpha K minus 1 V2, and so on, alpha K minus 1 Vn. That is for all the vertices. Suppose I have alpha K minus 1 value. How do I find alpha K V1, alpha K V2, and so on, alpha K Vn? From this vector of values can be found out using this relation. Okay, you will have a neighbor and the minimum cost of that neighbor you take and then compute the value corresponding to it. This is how I am using alpha K minus 1 value of all vertices to find the alpha K value of all vertices. Okay, this is the way I proceed with the computation. This is the key equation that I use in the derivation. Is this clear? Is this clear why I get alpha K minus 1 U here? This must be minimum. This portion must be minimum. If that is not minimum, I can replace it with something smaller and I will get something smaller to V. Smaller to V I cannot get. S to V, this is the smallest. Therefore, nothing smaller is possible. Therefore, no smaller part is possible from S to U. That means S to U, it should be alpha K minus 1 U. This is the argument. Is this clear? Have I answered your question, Akansha?
She has left, might have joined from
Some other meeting or okay, that is okay. So, what is the time now? 3:40, yeah? Okay, we have another 10 minutes. We can definitely interact 10 more minutes. 3:50, I have to leave for another meeting. There's another
May I ask, Banda?
10 more minutes, definitely I'm here. If you have any question or if my explanation...
Hello?
Yeah, please, go ahead.
Yeah, so one thing I want to ask that when we are in the process of finding all pair shortest path problem and we are discussing the algorithm 1 to 5, you may say.
Yeah.
So so in first algorithm we are using using the fact that the Bellman equation for bounded path, and in the second algorithm we are concerning with the matrix multiplication interpretation of it, and
Exactly.
that. Yeah, and then in the third, you may say that continuation of path, concatenation of path,
Exactly.
and so on. Be using some kind of abstract thing again and again to make it, I think, to make the complexity of it, to reduce the
Yes,
complexity of it.
exactly.
So,
N power 4, n cube log n, and then we made it into n cube finally. You are
so
right.
yeah, so to analyze the complexity of an algorithm, it's a good kind of a example. We may take that how the things evolve with the time.
Yes, very true. That is how things happen. Normally,
So
when a problem is encountered, first we will get some solution, and probably we will publish it, or we ourselves will think, can we do something better? Whatever the best comes to our mind, we publish. But somebody who is reading, he will think in a different way, and he will come up with a completely different way of solving it. And then he may publish the better algorithm. And in this way, algorithm comes from the minds of anybody in the world. You have already seen in any basic data structure and algorithm course, just for sorting, you have heap sort, you have bubble sort, you have selection sort, you have insertion sort, you have merge sort. Each one will look completely different. It is the same problem. Even for simple arranging the n numbers, you can see how many different ideas have come in the minds of humans and how they have made more and more efficient. Right? This will always happen for any important problem. We will first come up with some solution, then we will make it better by thinking, and then we will apply new technique and make it further better. And in this way, the algorithm area will keep growing, keep discovering better and better algorithm, and it will grow. So fortunately, our algorithm as an area of computer science is only 50 to 60 year old. It is not like mathematics, like geometry, which is 2000-year-old, where if you go to a library, one row full of math book will be there. But for algorithms, we are only 40 to 50 years old, and most of the problems we would have got recently studied something and improved upon it, got a data structure and all. So fortunately for us, the basic materials are somewhat compact and easy for us to trace the progression, trace the way in which better things have come in the recent past. That's what this course explains. Some of the interesting problems and the way in which a series of good ideas have developed for better solutions. You are right. Your observation is right. This is one
so
such sequence.
so I just want to ask this thing, that how we can improve that kind of thinking in some other problem that we encounter.
See, creativity has no formula. We can only illustrate good way of doing things, right? It is like, I can teach you Bengali, I can teach you Tamil, I can teach you English, but I cannot teach you to write a poem. I can give excellent examples of a poem, but poem writing is your inner creativity, your restlessness. There is some idea that bothers you, you intensely think, you use your own language and then create it. Can I teach you to write poem? I can explain example poems, but writing poem as a creativity has to be done by the individuals. It's innovation. It comes from your mind. So what this course will do is expose a lot of good examples and techniques with the hope that they will all create mental impression. And then when you get a problem, you may think, maybe if I take this approach, it should work. Maybe if I take this approach, it might work, and so on. So first of all, you need an exposure to a broad spectrum of techniques that has been found in the past and it is working well. Only then you will have a head start. If this kind of exposure is not there, when you have a problem, think of an algorithm means what will you do? Where will you start? Now at least you will think, can I do incrementally? Can I use some matrix approach? Can I use some divide and conquer? Can I do some dynamic programming? Various thinking now at least comes to your mind and you attempt. Maybe you will be successful in one of the approaches. So the idea is to expose a variety of techniques that builds strength in you. Remember, it is going to build only strength in you. Mastering is individual practice, right? That's the key point we should be aware of.
Sir, actually, I would like to add a little bit here. I mean, the question is very, it's a fantastic question. I mean, how can we improve upon such things? I've been thinking about this for a long time, and what I've come to observe is that every approach that humans have ever, used to solve a problem that has been derived from the nature itself. I mean, in electronics and electrical engineering, everywhere matrices are, a fundamental structure of their computation. So I think that the way in which we should do things is to look at 100 examples and try to, that's a hit and try thing. I mean,
Exactly.
that
It's
takes
just
time.
that. I mean, can we say for this problem only this technique will work? We can't say this. Can we say that all techniques I have tried? No. You have tried one or two. Maybe there is some other technique that works which we are not aware of. But somebody who knows about it discovers it and then he publishes it. That's how many things have come. So many algorithms have come. How? Through the creativity of various individuals at various parts of the world. Therefore, creativity has no formula, but what we can do is by observing a lot of good examples, we can probably get mental impression, inspiration, ways to think. Some approaches may come up in our mind with the hope that it leads to a good solution. It can only be hoped for. You cannot say for this problem from Monday to Friday, you think Saturday you are going to get an answer. No way. There are problems which people struggle for 2 years and they don't get a solution. And one guy comes and solves in 1 week, and then all things are happening in creativity. Therefore, the summary is creativity has no formula. It has to be individually explored, tried, as somebody pointed out, hit and miss. Try this approach. If that doesn't work, try some other approach. We have to keep trying it until we get a success. Right? That's
Yeah, thank you so
basic
much.
fact of nature.
Sir, just one more thing, sir. There are just 2 minutes remaining, so I just want your opinion on something. I mean, from the year 2024, 2023, there's been an AI hype right now, and everybody is trying to get into AI and machine learning and data science. I wanted your opinion on this, your personal opinion on this. I mean, do you think that this is just hype, or I mean, the real work is being done? I feel that the people who would have made it into AI 10 years ago would still make it into AI today because the skills required are highly mathematical from my perspective. But I see people today who just, know how to write few things in Python, and they just start calling themselves AI ML developers and researchers. So what is your take on that? I mean, I still value books
See,
over coding.
any sweeping generalization will reduce the effect of the statement and problems. There are many people who learn only Python and they think that they have mastered AI. That is there even in computer science. There are people who do only 6-week course in databases and they feel that they have mastered the databases. They would have done only Oracle training program. Does that make them a database expert? No. You may learn 6 weeks program in C, C++. Does it make you a software engineer? No. Basically, there are various wrong concepts and notions and other things are involved. For any body of knowledge, systematically learning from foundations to basic techniques to solid theoretical reasoning to all these advanced things, only when you do, you have a mastery over the subject. Otherwise, you will have a working knowledge that doesn't make you an expert, right? Even a school dropout is repairing your scooter and car. Will you call him an automobile engineer? No. Automobile engineer knows the principles, concepts, ideas, engineering mechanisms, and other things. The school dropout who is servicing your scooter, he knows only some working principle and then he applies it. These two are very different. Therefore, we must know to distinguish between a service person from a professional engineer. AI ML done at a professional high grade level is as deep as computer science. It's like any other branch. People who are expert in cryptography are also go deep in that. People who are expert in distributed system go that way. Therefore, why blame or bias AI ML? AI ML is another branch of computer science which requires advanced attention like any other branch of computer science. Some branches will pay you more, some branches will pay you less, and that is a market value. The market value can go up and down. Blockchain was big hype some time back. Now nobody cares about it. So is blockchain a good area or a bad area? let's not mix the job opportunities and other things and half-baked knowledge and other things all put together. We will get confused idea. So we will respect a body of knowledge for its content. If you want to learn them seriously, make progress, be creative. Okay, so I stop at this point, and we will have probably one more interesting online session maybe next week, and then we can continue our discussion. If there are enough interest in online meeting for 1 hour, I will come like this and generally talk about the subject as well as any other question that you may have on algorithms. Okay.
Okay, sir.
Yeah,
Yes, sir.
yeah, it's a great thing to do there.
Most welcome. Most
Yeah.
welcome.
And
Thank
thank
you,
you so
sir.
much.
Thank you for your
Yeah, I
suggestions.
appreciate, and thanks for your warm words on the course. Any doubt you have, get back to me.